Right, so now we'll talk about subspaces. We will be studying the space Rn, that is, the set of n-dimensional column vectors with entries coming from R. Okay? In other words, the entries of the column vectors are real valued. Now we continue our study of matrices by considering a class of subsets of Rn called subspaces. So you can think about a subspace as a subset of Rn. It's not true. Now we'll define subspaces rigorously, but for the moment, think about subspaces as subsets of Rn. Now, why are subspaces useful? Why do we study them? Because they arise naturally in real-life applications. For example, when we solve a system of n linear homogeneous equations in n unknowns, we will see that the row space, column space, and the kernel, the null space of the coefficient matrix, that is the matrix A in AX plus B. So we can characterize the solution of X through the row space, column space, and null spaces. They have a lot to tell us about the solution. We will also study the concept of linear independence of a set of vectors, which gives rise to the concept of the so-called subspace dimension. So linear independence is going to tell you pretty much a lot of stuff about the subspace you're working with. So now let's rigorously define a subspace. We say that a subset S of Rn is a subspace of Rn if the following three conditions are satisfied. What are they? First of all, the zero element or the zero vector belongs to S. That is, 0 falls inside S. This is 1. 2, S should be closed under vector addition. That is, if I grab two vectors from S, let's say U and V, then U plus V has to fall inside S. For any U and V, I pick an S. So if you find me one counterexample such that this is not satisfied, then we stop here and we say S is no longer a subspace. And last but not least, S should be closed under multiplication. That is, if I grab an alpha in R and the vector U in S, then alpha U should again fall in S. Okay? If you can find me an example where this is not true, then we say stop and we conclude that S is no longer a subspace of Rn. Now, those are the three conditions required to say that S, that is itself a subset of Rn, to be a subspace of Rn. You can think about Rn, actually no, it is true that Rn is a subspace itself. Why? Well, grab the zero vector. Rn contains the zero vector, right? A vector of all zeros will fall in Rn because 0 is itself an element of R. If you grab any two real vectors, you add them up, the result will be again in Rn. Furthermore, if you grab a real number and multiply it by any vector in Rn, the result will fall in Rn. So that's why Rn is a subspace of itself. And we will refer to Rn as the vector space. You can think about it as the universe where our study is going on. Okay? Note that this is not the only vector space. There's millions and billions other vector spaces that we can form. For example, you can think about the complex field, the Galois field, and so on. You can generate a lot of vector spaces in those domains. Okay? Now, the complete definition of a vector space is really very general, and we will not work with it here. We're going to keep stuff at this level, and I'm not going to, complicate stuff more. I'm just going to give you the idea of subspaces. In future lectures, we will introduce stuff that has to do with vector spaces, such as the Fourier series. We're going to see an example on that. Now, let's give an example over here about subspaces. Let's say I've got an n by n matrix, and I'm interested in the set of all vectors x that fall in Rn, meaning that the set S contains all trivial and non-trivial solutions of the homogeneous system Ax equals 0. Now the question is S a subspace of Rn? Let's find out. So 1, we have to ask ourselves the question, does the 0 vector fall inside S? Well, let's see. First of all, 0 is in Rn, okay? And A times 0 equals 0. So 0 is actually a solution of Ax equals 0. Hence, 0 falls in S. Now 2, let's ask ourselves, if I pick U and V in S, does U plus V fall again in S? Well, let's pick U and V in S. Let's see what we get. If U is in S, then AU is 0 for a real column vector u. Same thing, if v is an S, then AV is 0 for v in Rn, okay? What about u plus v? Does it fall in S? Well, those two indicate that a u plus a v is 0, right? Adding those two equations. Well, factor a as a into u plus v is 0, and this guy falls again in Rn. If you add two real valued vectors, you will get a real valued vector. So u plus v satisfies this. Hence, we can say that u plus v falls in S. Now, if I pick an alpha in R and u in S, does this give me that alpha u is also in S? Well, let's see. We've got this. So if u is in S, that means that AU is 0, right? For u in Rn. Well, let's multiply both sides by alpha. Let alpha be in R, and let's multiply. We get alpha AU is 0. Well, we know that alpha, we can play around with it due to one of the properties we mentioned in previous lectures. So I can absorb alpha into u as such. A times alpha u is 0. So alpha u also satisfies this equation. Hence, alpha u is an S. So S satisfies all three conditions that qualify it to be a subspace of Rn. Hence, S is indeed a subspace of Rn. Note that S has a name. It's not any set. This set is actually called the null space of A. Okay? It tells you, and it's denoted by n of A. It is a set containing all vectors that null out or zero the A matrix upon right multiplication. Also, remember in the previous lectures when we talked about solving a system through Gaussian elimination, and hence we get a row of all zeros, we started parametrizing one variable with respect to the other. Well, now we can characterize this inconsistency in terms of subspaces. So imagine you've got a matrix A, you're solving for, I don't know, AX equals 0, where your A is 1, 2, and 2, 4. Okay, and you're performing, Gaussian elimination. You form your augmented matrix, and your R2, for example, you replace it by R2 minus 2R1, and hence you get 1, 2, 0 in the first row and all zeros in the second row. That said, you have infinitely many solutions, and therefore you can characterize your solutions as x1 plus 2x2 equals 0, right? Well, the set, actually, the subspace comes in the following. The set of couples x1, x2, such that x1 plus 2x2 equals 0 is actually a subspace that is the null space of A. This is how you characterize the null space of a matrix. Note that if you have a matrix with no zeros here, the null space will be the singleton 0. So for example, if your A were to be 1, 0, 0, 1, the identity matrix, then there is no vector that could null this out. There's no non-trivial vector that could null this out, and hence the null space of A is just the 0 vector, the trivial solution. Okay? Now, note that how we usually characterize subspaces by some linear system where the variables are allowed to move in R. So in this case, we've got two variables, so they move in R square. This representation is actually referred to as a linear combination of x1 and x2. Okay? So what is a linear combination? It's really when you linearly combine your variables. So that said, if your set of variables, let's say x1 down to xm, fall in Rn, then the expression c1x1 plus down to cmxm, or if you want, you can write it as sum over k, going from 1 to m of the quantity ck, xk. This thing is said to be a linear combination of x1 down to xm for a given choice of c1 down to cm, okay? Now, furthermore, we're going to introduce the span. So the span is the set of all linear combinations. That is, if you're given m vectors, x1 down to xm, those are given, and you're asked to compute the span of this collection or this set. Well, what do you say? What is the span? The span of a set of vectors x1 down to xm is actually equal to this set of c1x1 plus down to cm xm, where c1 down to cm belong to R. Okay, so you grab the vectors, you multiply each by a scalar, then you add them up, and you allow all the scalars to move in R. Okay? Even more, the span is a subspace of Rn. Keep this in mind. A span is always a subspace. It's easy to verify that it falls in Rn because each and every xk falls in Rn. It satisfies the three conditions that qualify it to be a subspace. I'm not going to give an example on spans and linear combinations yet. I'm just going to define one thing that totally depends on the span, thus the linear combination concept, and only then I'll give an example. Okay, so let's define two terms. So given a square matrix, we can define the so-called column space and row space. So the column space, if you look at A as a bunch of columns, A1, A2 down to AN, then the span of the columns of A actually have a name. It's called the column space of A, right? Now, if you want to regard A by looking at its rows as R1, R2 down to Rn, well, you can do that. And you can also look at the span of the rows of A, which will be referred to as the row space of A. Both of those are subspaces because the span is a subspace, and both concepts will turn out to be useful later on. Okay, let's say you're given the identity matrix. Do an example on row and column spaces. So 1, 0, 0, 0, 1, 0, and 0, 0, 1. The identity matrix is the identity matrix of size 3 by 3, and we will denote each column by E1, E2, E3 respectively. So EK stands for the kth column, guys. E1 to E3. Now, the column space is the space spanned by the columns of I, using the definition that is the span of E1, E2, E3. Okay, which is using the definition of the span, it is C1E1 plus C2E2 plus C3E3, where my CKs are in R. Now, what is this space? What do we get? Could you write it as something else? Well, of course. Since E1 and E2, and you can rewrite C1E1 plus C2E2 plus C3E3 in a different way. How? Well, C1E1, C2E2 plus C3E3 is actually C100, since E1 is 100. Then C1 times 1 is C1, and C1 times 0 is 0. Likewise, C2E2 is 0, C2, 0, and C3E3 is 0, 0, C3. Right? This is equal to a vector containing C1, C2, and C3. Thus, we can write this as this. Okay, so you're telling me that the span of the identity matrix is a column vector containing elements from R. What does that mean? It simply means that this is nothing other than the set R cubed. So the column space of I is R cubed. And likewise, since I is equal to its transpose, I is I transpose, then the rows of I are the columns of I, and hence you can say the same thing about the row space of I. You do the same steps and you will get R cubed. And by the way, the columns of I are referred to, they have a name, and they are referred to as standard basis vector. Right? It is a standard way of expressing those vectors are the standard way that me and you use to represent any vector in R cubed. So this is a standard basis vector of R cubed. And why is that? Well, it's because any vector, let's say C1, C2, C3, could be expressed as a linear combination of the standard basis vector. How? It's this expression over here. So you can say C1 times E1 plus C2 times E2 plus C3 times E3, thus representing a vector in R cubed in this basis, E1, E2, and E3. And by the way, if you have another matrix not written in the standard basis, and it turns out that its column space is R cubed, that means the span of the column space, span of the column vectors of this matrix is R cubed. That means any vector in R cubed could be expressed in the basis defined by the column of that matrix. We'll see an example further. Let's give another example on this topic. Say I've got the following equation: 2x minus 3y plus 5z is 0. This equation actually defines a relationship between the components of the vector xyz. What is the relationship? It's this one, right? This is the relationship between the components of the vector xyz. Now, let's say we're interested in finding the subspace S of R³ spanned by all such vectors. How do we do that? Well, if this vector falls inside the subspace that we're interested in, that means that you can say that this subspace, it contains all vectors x, y, z such that 2x minus 3y plus 5z is 0. Let's say we want to express this subspace differently. Well, we can use reparameterization. That is, since we have one equation, then we need two free parameters out of the three. Without loss of generality, let's choose y and z. So we'll keep them as is, and we'll try to express x as a function of y and z. So how do we do that? It's simple. 2x is 3y minus 5z, which means that x is 3 over 2y minus 5 over 2z, right? So I'll copy it here, 3 over 2y minus 5 over 2z. So note that I have two free parameters, y and z. Well, let's decompose two vectors, one in terms of y and the other one in terms of z, right? So where is y found? It's found in the first and second entries. That means that the third entry is 0. The second entry is 1 and the first entry is 3 over 2. Likewise, z is found in the first and third entry. That said, the second entry is 0. The first entry is the coefficient multiplied by z, that is minus 5 over 2. And the last one is 1. So the subspace S, we can say that S is spanned, it is the span of two column vectors. The first one over here and the second one right here. So 3 over 2, 1, 0 and 5 over 2, 0, 1. And unlike what we had over here, that the column space or the span of E1, E2, E3 is R³, well, guess what? This span is not R³. It suffices to see that the number of vectors is not 3. You need at least 3 vectors to represent R³, right? Now we're starting to see how subspaces come in play. So that means if I have a drawing as such, I'm in the XYZ plane and all this is R³, well, how does this span look like? So the first vector, 3 over 2, let's say this is 3 over 2, 1, this is 1, and 0. So this is the first vector, 3 over 2, 1, 0, right? And the second one is minus 5 over 2, 0, and 1. Guys, a 1 over here, right? So the subspace S is actually the hyperplane containing, you can see it, you can view it as the hyperplane containing both vectors, right? Now, problems arise as to indicate whether a certain vector falls inside a subspace or does not fall. Well, let's pick a vector. Let's say I've got the vector 1, 2, 3, and I want to know if the vector 1, 2, 3 falls inside S or not. That's the question. Well, if you can write 1, 2, 3 as a linear combination of those two vectors means that it does fall in this. A way to verify is that remember how we started. S was actually a 3D vector such that the relation between its components is this. Now you ask yourself this question, do we have the same relationship in the vector 1, 2, 3? Well, let's check. 2x plus 3y plus 5z is equal to, if we evaluate x to 1, y to 2, and z to 3, is 2 times 1 plus 3 times 2 plus 3 times, this is not 0, and hence 1, 2, 3 does not fall inside the span of those two vectors. This means that we cannot find two scalars c1 and c2 such that the vector in question 1, 2, 3 is equal to c1 times the first vector in the span plus c2 times the second vector. This is impossible. This is what it means. And you can actually see it coming from here. The second equation tells you that C1 must be 2 and that C2 must be 3. Well, if you pick C1 to be 2 and C2 to be 3, then it is impossible that 2 times 3 over 2 plus 3 times minus 5 over 2 is 1. This is not true, okay? So that's it for this lecture, where we talked about subspaces of the vector space Rn. In particular, we gave the 3 main characteristics that qualify a certain subset of Rn to be called the subspace of Rn. That is, the 0 vector should be in the subspace. If you grab any two vectors from that subspace, the addition should also fall again in the subspace. Also, if you scale a vector in the subspace, it should remain in the subspace. We gave an example through the null space of a matrix A. That is, the null space of A is itself a subspace of Rn. We saw an example where the null space could be the 0 vector, right? And also we introduced topics such as linear combination and the span of a bunch of vectors. And it turns out that given a matrix A, we denote the span of its column vectors as the column space of A. Likewise, the span of the row vectors of that matrix is called the row space of A. Now, it turns out that sometimes, the column space of a certain matrix could cover all Rn and could not, right? So, in some cases, which are not coincidence, we will see those stuff in more details later on. It turns out that the subspace could not be Rn, as is the case here. So the blue subspace, you can see here, is a subspace that falls in Rn but does not cover all Rn. And to see this more clearly is that we tested for the vector 1, 2, 3. We picked any vector at random, let's say 1, 2, 3, and it turned out that this vector does not fall in S and hence could not be written as a linear combination of the elements of its span. Thanks for watching. If you enjoyed this lecture, please consider subscribing to my channel, liking this video, sharing it on social media, and if you have any questions whatsoever, just leave a comment down in the comment section below. I'll make sure I'll get to it as soon as possible.